Alright, hey guys, back at it again with Physics 2-7. This time we're going to do 2018. I know I'm uploading this 3 hours before the exam, but hopefully this helps somebody. Okay, so, per usual, we have a circuit question right off the bat that we can easily do, I would say. So, we know all the R's and the V's. That's nice to know. So we're most likely going to be using this equation for this one. So I'm going to go ahead and just start from battery 1. Draw a current going this way towards resistor 1. It's going to go down, and then it's going to split between here and here, so I2 and I3, and it's it'll be coming back to I1, and then it'll go up across I4 as I1 as well. Okay, so what we need to do first is state that I2 plus I3 equals I1. Right? Okay, so now we need our loops. So our first loop will be here, and our second loop will be in here. So loop 1, and we're just needing to find the amount of equations to solve this, so we don't need to do anything more than that, but also we'll get our electric field lines from inside the batteries. Okay, cool. So this first loop is going to be going against battery 1. It's going to go in the same direction as I1R1 plus I1R2, or really I3R2, let's say, since it splits at that junction. And then it'll be going in the same direction as V2, and then plus I1R4. That equals 0. Then we have the second equation, which is going to be, or the second loop, that's going to be going in the same direction as battery 3. It's going to be going in the same direction as current 2 over resistor 3. And it's going to be going against current 3 over resistor 2, which equals 0. Now, we could solve this, but we don't need to. This should be enough. There we go. That way, there's no more notifications coming through. But then, that should be it. Yeah. You just move this down here. You would probably want to include the current 1 equation as well, since that would be useful for actually solving for the currents. Okay. Now, we will move on to the next question. So in the circuit below, all the RC's and V's are known. The circuit was put together a long time ago, so it's in a steady state with the switch closed. Find the currents in each resistor and the charge on the capacitors. All right, so that's part A. So just draw our currents real quick. Okay, so it's going to come out of this battery and go towards resistor 1, and then when it hits this junction, it won't go down because there is a capacitor there, so it's just going to keep going as current 1. It's not going to split. Same thing here, it won't go towards the capacitors if it's in steady state, so it'll just keep going around as I1, and then it'll come back in as I1. Cool. So now I got to put charge on the capacitor. I would imagine this is what it's going to look like. Because if before it was in steady state, the currents would be entering this junction, and hitting the positive plate of the capacitor, and then continuing on, and then they would go across the switch and then down to this capacitor, and it would probably build charge on this side, I think. Yeah, okay. Then we need our loops, so we'll have loop 1, loop 2, and loop 3. So for loop 1, which will be this one, we'll have negative V plus IR1 plus C1 over, or sorry, charge 1 over C1. So in this question we're using IR, or V equals IR, and V equals Q over C. So then we'll have Q2 over C2, and that'll be the first loop, equal to 0. For loop 2, we have IR2 minus Q1 over C2 equal to 0. And 3 would be I times R3 minus Q2 over C2, which equals 0. Cool. So now we need to find the currents in each resistor and the charges on the capacitor. So we can solve for these, and then we can substitute these values in for this. So negative V plus IIR1 plus IR2 plus IR3 equals 0, which means I would equal V over R1 plus R2 plus R3. Then, if we move these down here, we'd have that Q1 equals IC1R2, and Q2 equals IR3, or IC2R3. Then we just need to plug in I for these two, which I'm not going to do, but you get the point. Now that's part A. Part B is asking about the switch, which the currents would pretty much be the same here for this question. Still, they wouldn't enter this junction, and it would just keep going around to R2. And then you would have still, if the switch is open, the current wouldn't run across it, but even if it was closed, obviously. So basically what the switch is doing here is it's basically taking away this wire from the circuit. It's as if it wasn't ever there. So it kind of conjoins these two boxes. Okay. Then just keep going around as usual towards the battery again. Again, the charges might actually be different on the capacitors this time. Well, if the switch is then opened, so never mind, the charge on the capacitor would be the same. Because we're basically taking this thing and opening the switch. So then we would have positive and negative charge the same. Okay, cool. Now, loop 1, we only need 2 loops now because we really only have 1 to 2 seconds of this circuit, so we can put a loop here and then put a loop here. So we have negative V plus IR1. Probably going to have the same equation for the first loop. Then we have loop 2 which is just going to be IR2 plus IR3 minus Q1 over C1 minus Q2 over C2. It's cool, we're kind of adding these two together to get this second loop. Yeah, so if the switch is opened and enough time passes, obtain a sufficient number of equations so that you could solve for the currents and the charges on the capacitors. Okay, so this is all we needed to do for the second part of this question, because we are just wanting to find the equations for it, not solve it. So that's good. All right, cool. Now let's move on to the next question. All right, so an infinitely long insulating cylinder radius R1 has a charge uniformly spread throughout its volume so that the charge per unit volume is rho. All right, so we're given rho in this question. A conducting cylinder with inner radius R1 and outer radius R2. So it's inside a conducting cylinder, which will be important. Find the difference in the electric potential between a point on the axis, so here, at the center of the cylinder, and a point at distance 2r2 from the axis of the cylinder. Okay, so what we're going to need to use here is we're going to use Gauss's law. Q enclosed over epsilon. We're going to need electric potential difference. We're probably going to need the fact that Q enclosed equals rho times V, and we'll probably need the volume of a cylinder, which is pi r squared L. Okay, so our first step here is to get an equation for the electric field. So Gauss's law will be used for that, which will end up being E times 2 pi RL, which is the surface area of the cylinder, equal to Q enclosed over epsilon, which we can then solve to be Q enclosed over 2 pi RL epsilon. Right, okay, so don't forget your vector. All right, so what we need to do now is solve for Q enclosed, or find the electric field at different points on this object, so that we can then use that in the electric potential difference question, or part, to find the answer. So step one is to do when the radius is less than R1. Now this is where the object has charge, and so it's Q enclosed is going to depend on where we are along the radius given the Gaussian object size, depending on its radius. So what we could do first is say that Q enclosed here is going to equal the integral of from 0 to r of rho dV. And as we know, the volume is this, so we can just take the derivative of that with respect to r and get that. Okay, so then we'll have 0 to r rho times 2 pi RL dr, which would then come out to just be rho times pi r squared L. Right? Yeah. Okay. Cool. So that's the Q enclosed there, which we will then put in the electric field equation here as electric field 1. And so we'll have rho times pi r squared L, because we just solved for Q enclosed, so we can just plug it in, over 2 pi RL epsilon, which will just equal rho r, because the pi and L would cancel, over 2 epsilon IR for the electric field. Now, when R is between R1 and R2, since this is a since it's inside a conducting cylinder, we know that the space between R1 and R2 is going to have 0 enclosed charge, which implies 0 electric field. So that's easy. Then we need to go, since we're wanting the electric potential difference but beyond the object itself, we need to find the Q enclosed, or the electric field outside of the object. So how we do that is we find the electric field when R is greater than R2. And what we do for that is, when we're trying to find Q enclosed, we only want to integrate we won't want to integrate along the radius until the object that has charge ends. And so in our case, the inner cylinder has charge. So we would start at a radius of 0 and go until we are outside of the object that has charge, which would be radius R1. So when we're trying to find Q enclosed beyond R2, we only need to go from 0 to R1, because this is the only part of the object that has any charge. So then we just do the same equation here. Rho times 2 pi RL dr, which then comes out to be rho pi R1 squared times L, which we can then put into the equation for electric field to get, it'd be rho R1 squared, pi and L would cancel out on the numerator and the denominator, because we're putting it in here, which would leave us 2 epsilon, I imagine. I think. Let me make sure. So rho, pi would cancel, R would stay. Oh, yes, there'd still be an R in the denominator. Okay, so that's our electric field 3. And that's all we really need, because it's the electric field beyond the wire. And again, I just want to reiterate that when we're trying to find Q enclosed beyond an object, you only want to integrate as far as the object that has charge. In this case, we're only integrating along the radius of the object that has charge, even though we are going to R2, because this is the only thing that would have any charge. So now we want to add all these electric fields together to get to do this, to define electric potential difference. So we're going from a point on the axis to a point 2r, R2 away, which would be the negative integral of 0 to 2r2 of these two added together. So we'd have rho r over 2 epsilon naught dr minus 0 to 2r2 of p r2, or r1 squared, over 2r epsilon naught dr, which would then be equal to, so we can take out these constants, and we would have, this would go to the second power, and then it'd be 1/2 times 2r2 squared. Let me put round brackets there. and then 0 would obviously cancel out. Okay, minus rho r1 squared 2 epsilon naught and that 1 over r that's left over when we take out the constants here would become ln 2r2 minus 0. So ln 2r2 minus ln of 0. Something doesn't feel right about that, but oh, I made a mistake. Right. We need to do the second one from R1 to R2. Or no, this would be from 0 to R1, and then from R2 to 2R2. And the reason that is because if this had an electric field, the integral would be from R1 to R2. And since we have different electric fields at these different points, we need to integrate along those radii. Almost forgot that we had to do that. So that would make this ln of R2 minus ln of R2, or ln of 2R2 minus ln of R2. And that would make this 1/2 R1 squared. And that would be our final answer for the equation. So yeah, really the secret here is just kind of like using these inequalities to set up the bounds for the integrals. It's a good thing to remember. I almost forgot to do that. Okay, that should be an answer. Yeah. All right, so next question is we have a spherical shell with inner radius RA, an outer radius RB, has resistivity rho 1, is inside a second spherical shell with an inner radius RB and an outer radius RC with resistivity 2. Current I is flowing radially out uniformly through the two shells. Find the difference in the electric potential between point A and point B marked on the figure. Okay, so we're most likely going to need I equals VR for this one, where resistance equals rho L over A. And then we'll end up having we'll probably also need this equation for the electric field, which is rho J, where J equals current over A. So the first step here is finding the resistance for each section. So between RA and RB, we're probably going to need to do R equal to rho 1 times 1 over 4 pi r squared dr, where dr is L and 4 pi r squared is A, which will come out to be rho 1 over 4 pi let me think about this real quick. I think, honestly, we might not actually need to do this because we're given a current. But not a voltage, though. That's the only difference, though. So what I think we need to do here is, if you know row 1, oh, duh, we don't need to do this at all because we have current. So the electric field, we can just say is row 1, because we're given row 1, times I over 4 pi r squared. Yeah. That makes sense. Okay, so then between RB and RC, we have row 2 times I over 4 pi r squared. IR. Yeah, okay. Well, it's way simpler than I thought it was going to be. I was thinking we needed to find resistance to then plug into this, but we don't have voltage, so we can't really use that concept. I don't think. So then we need to use these in the electric potential equation, which we're asked to find between A and B, which is radius A to radius RC. So we would have RA, or RC, minus VRA, which will be negative RA to RB of row 1 I over 4 pi r squared dr minus RB to RC of row 2 I over 4 pi r squared dr. Okay, so that'll just come out to be row 1I over 4 pi times 1 over, and the negative disappears because this is a negative exponent we're adding to it, and then it's dividing by that new number. So we divide by negative 1, so the negative gets canceled, and then we just have RB minus 1 over RA. Same thing here. We'd have row 2I over P, which would be 1 over RC minus 1 over RB. And you just check that that's the answer. Okay, appears to be the answer. Nice. So, there we go. And that is the whole exam. I want to do one more problem though from 2019. Since it's kind of like this question but for a sphere, I thought that might be useful as well. So let me save that and then we can do this one here. All right, so we can do this next question as well. So, a spherical conducting shell has inner radius A and outer radius B. Its center is a sphere of radius d that has a charge q uniformly spread throughout it. Find the difference in the electric potential between a point at the center of the sphere and a point 2b from the center. So I'm saying this is probably 2b. Yeah, because this is A and this is B. So again, we're going to Gauss's law here. And then we would need electric potential difference, which is negative R2, the negative electric field of dr. And then we probably also need the volume of sphere. So, okay. So first step again is to find the electric field using Gauss's law, which we know comes out to be E times 4 pi r squared, which are the concentric spherical shapes that we're taking out from the center, which is going to be equal to Q enclosed over epsilon naught, which we can then solve for electric field, which is 4 pi r squared epsilon I r. So that's our general equation for electric field. And now, since we're trying to find the electric potential between this central point here to 2B, we need to find that electric field. We need to find the electric field at different radii, just like we did with the cylinder. So, our first equation is going to be when our first electric field is going to be when R is less than D, when the Gaussian sphere is less than D. And so we'll do another thing to remember here is that an important detail is that we were not given rho, so we have to create rho for ourselves, which isn't that bad. So rho for this object would be Q, because we were given Q, divided by the volume of the object that has charge, which would be 4/3 pi d cubed, because the object that has charge only has a radius of d. Right, so that's what rho would equal. So we'd have Q over, just make sure I'm doing this math right. We can flip this up. Yeah, so it should be, okay, cool. All right, guys, it's been a long day. So this would end up being 3Q over 4 pi d squared, I believe. Yeah, because if that's 4 pi d cubed over 3, that's Q over 1, that would flip up to the top, and that would flip up to the bottom, and this would be d cubed. Okay, so that's rho. And rho should be a constant value because we're given that charge is uniformly spread throughout the object that has charge, which is the object with the radius d. So to find Q enclosed, we need to do the integral from 0 to r. And the reason it's r is because we want a variable radius since we're inside the object with charge. Right. So to kind of like sum up all the Gaussian objects that are enclosing the charge, accumulating them. Right. So that'll be rho times dv, and we know that dv equals 4 pi r squared dr. So we'll have 3q over 4 pi d cubed times 4 pi r squared dr, which will then end up being, the 4's will cancel out, the 3q over d cubed would come out, and that r squared would evaluate to be 1/3. Yeah, that's right, I think. R cubed. I hope that's right. It seems right. So the 3's would cancel, and then that would leave us q over d cubed r cubed for charge enclosed. And so our first electric field would end up being q r cubed over d cubed over 4 pi r squared epsilon naught, which would then be, with r's would cancel, so we'd have qr over 4 pi d cubed epsilon naught ir. That seems vaguely familiar. So, okay, now we want to integrate between, now we want to find the charge enclosed between D and A, which would be I'm trying to think how I want to do this question. I think, so since that's not the conductor, the charge enclosed here should just be Q, I think. Yes, which would mean the electric field here is just Q over 4 pi r squared epsilon naught D. IR. I think so. And then between A and B, there would be zero charge because that's a conducting object, which means the electric field there would be zero as well. And then R beyond B, we would want to integrate Q enclosed from 0 to D. Just like in the cylinder question, we only go to the up to the point of the object that has charge, which we would then have 3Q over 4 pi D cubed times 4 pi r squared dr, which would then be, we would have 3Q over D cubed 1/3 D cubed, which would then, those would cancel, leaving us with just a charge of Q. Oh, that's interesting. Cool. So then electric field 4 would just be Q over 4 pi r squared, I believe. Sorry if I don't sound super confident. This is a lot of electric fields, but it makes sense because of how the layers work. Okay, so then we need to add all these together and then integrate from 0 to 2b. So let's do that here. So 2b minus v0 would equal 0 to d for qr 4 pi d cubed epsilon naught dr, and then we'd have d to a for q 4 pi r squared epsilon naught dr minus yeah. And then I guess we would go from B to 2B, which would this be 4 pi r squared epsilon naught dr. Now before I go and do all the calculus, let me make sure that this is the actual answer and I'm not leading anybody astray. I actually don't even know if I've done this question yet at all. This is a new one, which I thought would be funny. Let's see. Okay, yeah, I haven't done this one. So let's just look at the answer and see if we did it right. So, okay, yeah, it looks like we did it right. Okay, so this would be negative, all the constants can come out, so we'd have 4 pi d cubed epsilon naught over 1 half d squared minus q over 4 pi epsilon naught. And then that would get rid of the negative because we're adding 1 to a negative exponent and dividing by that, which would be negative 1, which would then be 1 over d minus 1 over a. Could also take the negative out and swap those if you wanted to. That's what they did in the answers, I think. And then we would do the same thing here because it's the same electric field. So 4 pi epsilon naught 1 over 2b minus 1 over b. Okay, this is the final answer. I'm so glad that that actually was the right answer because something didn't feel right while I was doing this question. It might be the pita that I just ate, but maybe, I don't know. But yeah, so this is how we would do it. So basically, just find electric field using Gauss's law, and then find the different electric fields at different radii, starting with the object, starting from 0. And then add all of them together. Ooh, that was horrible. Y'all didn't hear that. I'll have to edit that as a video. And then once you add them all together, you can then take the electric potential difference. I thought it was cool that beyond RB, it's literally just Q enclosed. But it's always nice to just check with the calculus to see that Q enclosed is Q, or if it's not. Like, if I had done the integration for this one, it would most likely have canceled out the Q as well. But that's because the reason that it's Q, if anybody's interested in the actual physics behind it, it's that we're beyond the object that has charge, so there is no more need to accumulate Q enclosed. And that's the reason that there's a variable R in the boundaries of integration, or the limits of integration, sorry, so that it can vary. The Q enclosed would vary as the Gaussian sphere grows from radius r equals 0 to r equals d. But past r equals d, there is no more change, and it just becomes Q. Because everything past any Gaussian object with a radius greater than d is just going to contain charge Q, which is the charge of this object. I don't know, it took me a long time to figure that out, but that is kind of the concept that I think that makes Gauss's law so difficult, as the king likes to say. The king being Michael Cordell. So, yeah, that's the answer. This was question 4 in 2019, and then we did exam 1 in 2018. So, yeah, and then also just another quick concept to remember is, like, if you're not given rho, it's best to just, if we're told that the charge is uniformly spread, you can assume that rho is going to be constant, and so you can use the fact that rho equals charge over volume to make your own rho in the integrations that we do for the electric field. So, all right, guys, the exam's in 2 hours. I'm gonna kill myself, but I hope this video helped, and I'll see you for exam 3.